Screen is visible, students. Okay.
Yes, sir.
Okay. I'll do some more problems on real gases. Okay. This problem, determine the critical pressure of oxygen using the perfect gas equation and van der Waals equation. Okay. Take VC bar, that is molar specific volume is given as 0.0745 meter cube per kg mole, and a critical temperature is minus 118.10 degrees Celsius. Okay. So first you apply the ideal gas equation at critical point. TC VC bar equals to M R bar TC. Okay. So our aim is to find out critical pressure. That's why you have to apply the ideal gas equation for the critical condition. Okay. So PC equals to MR bar TC divided by VC bar. M is 1 kg because they have not mentioned anything. Okay, so you have to by default you take M as 1 kg. R bar is 8.3144, that is the universal gas constant, and TC is given, that is TC is minus 118.10 degrees Celsius. You have to express in Kelvin, that is minus 118.10 plus 273 divided by VC bar is given in the problem itself. Okay, just you substitute the value, get the critical pressure, that is 0.0745 is the molar specific volume at critical point. So after solving we are getting 17,287.25 kilopascal. You have to express in bar, it is 172.87 bar. Okay. And one more thing, we derived this derivation in van der Waals equation. Okay. That is um, R bar equals to 8 by 3 into TC bar divided by 2. This equation is you are obtaining in van der Waals constant. Okay, I derived this derivation. So R bar equals to 8 by 3 into TC bar divided by TC. So this is the equation related to the real gas. Okay, that's why you go through the van der Waals equation derivation properly. There you will get this equation, R bar equals to 8 by 3 into PC bar divided by TC. Okay, 8 by 3 is the value. This is the amount of deviation of real gas from ideal gas, and for ideal gas we are getting it is 1. Okay, hence we studied a limitation of van der Waals equation, where the whatever the results obtained is not accurate because the constant varies from zero point 0.2 to zero point 0.3. Okay, so this is the amount of deviation of real gas from ideal gas. So our aim is to find out PC. PC is 3 by 8 R bar TC divided by VC bar. So you remember this equation in case of real gas to find out the critical pressure. 3 by 8 R bar TC divided by VC bar. 3 by 8 R bar is 8.314. TC is the temperature at critical point. You have to express in Kelvin divided by VC bar. So we are getting it as 64.82 bar. You see. So how much deviation is there? Okay, by using the ideal gas equation, we are getting 172.87 bar. Using real gas equation, 64.82 bar. Hence, I said that real gases are those, okay, where the intermolecular forces of attraction and repulsion are taken into consideration. And in case of ideal gas, no intermolecular forces of attraction and repulsion are taken into consideration. Okay, and the real gases are one which obey the ideal gas laws only at low pressure and high temperature. Okay, so high temperature, or one more term is elevated temperature. Okay. So you see the uh, equation. Okay, so whatever value we are getting, it is a more accurate value. Okay, and here you see there is a lot of deviation is there. See how much is almost two times it is more in case of ideal gas. Hence, whatever the results we are obtaining using Van der Waals equation is accurate value as compared to the ideal gas equation. And here we are going to compare both ideal gas and real gas. Okay.
की मम्मी नाच के खबर
Hello. Mute your. Okay. You try to understand this problem.
brain
Okay.
is relaxed.
Okay. So this kind of problem is important. Okay. So I repeat once again this problem to find out the specific volume of carbon dioxide gas at 200 degrees Celsius and 60 bar pressure by using perfect gas equation and compressibility chart. So here same kind of problem you get, only they'll change the temperature and pressure value. Okay. So by using perfect gas equation and compressibility chart, the perfect gas equation is PV equals to MRT. So volume equals to MRT divided by P. So MR bar T divided by MP. Okay. So this is R equals to R bar divided by M. So those who are not understood understand how to see the tables and how to solve the problem using compressibility chart. Okay. So 1 into 8.3144 into 200 plus 273 divided by molecular weight of carbon dioxide gas is 44 into pressure of gas is 60 bar. Okay. So 0.01489. And using compressibility chart is most important. Okay. So in compressibility chart, we are having the reduced pressure and reduced temperature. So we have to find out the reduced pressure. Reduced pressure is actual pressure divided by critical pressure. Okay. Actual pressure is given 60 bar and critical pressure you are going to obtain from table C6 of page number 58 in thermodynamics data handbook. Okay. So you have to first find out the properties for carbon dioxide gas. Okay. TCR equals to 31 degrees Celsius, PCR equals to 73.85 bar, and rho CR equals to 460 kg per meter cube. So first you find out PR equals to actual pressure divided by critical pressure. Actual pressure is 60 and the critical pressure is 73.85 bar. So we are getting the PR as 0.812 value. Okay, this is 0.812 bar. Similarly, you have to find out the reduced temperature equals to actual temperature divided by critical temperature. Actual temperature is 200 plus 273 divided by 31 plus 273. We are getting PR equals to 1.555. Okay, so we are not getting 1.55 in the compressibility chart. Just you refer the nearest value, that is 1.5. And also PR we are not getting 0.812 in the compressibility chart. You have to refer the nearest value, that is 0.8. Okay, so this is the nature of compressibility chart. So PR equals to 0.8. Actually, in a compressibility chart, we are having 0.2, 0.4 like that. The 0.8 is here, and then TR is 1.5 here. So just you scroll up and you find out the intersection point of PR equals to zero point 0.8 and TR equals to 1.5. So intersection point is most essential. And then you take in the horizontal direction, just you find out the value of Z. So you're getting around 0.95, 96 like that. In most of the cases, you'll get 0.9 to 0.98. Okay, so that is the value what you are getting from the compressibility chart. So from that corresponding to pressure of zero point 0.8 and TR equals to 1.5, the value of Z is 0.96. Next, you have to find out the volume. Volume equals to Z dot T divided by P. So V equals to 0.96 Z, what we got from the compressibility chart. R equals to R bar by M into temperature T is 200 plus 270. Remember, you have to express in Kelvin, and P you have to express in kilojoules because 8.314 is in kilo units. That's why you have to express P in kilo units. 60 into 10 to the power of 1000. We get V is 0.0173. So you see, we are getting 0.01489 using ideal gas equation, and we are getting V as 0.0173 using real gas equation. Hope you understood the problems in real gas. Any doubts? William? William? Okay, I'll do some more problems on ideal gas mixture. Okay, you studied real gas. Now I'll do uh, how to do the problems in ideal gas mixture. Till now we studied ideal gases, real gases. Okay, now I'll do some problems on ideal gas mixture. Okay. A container stores 5 meter cube of an inert gas at 200 bar pressure and 290 Kelvin. Determine the mass, density, specific volume, and molar volume of the gas. Assume molecular mass or molecular weight of the gas as 28. Okay. So first, already you know the general gas constant or characteristic gas constant is given by R equals to R bar by M. So first, you have to find out general gas constant 8.314 divided by 28. Okay, because it is given in the Problem as 28. 28 is nothing but it is nitrogen gas only. 0.2969 kilojoules per kg Kelvin. Okay, next we have to find out the mass of the gas. Mass of the gas is given by PV equals to mRT. So M equals to PV divided by RT. Okay. So here remember, you have to remember very simple equation. PV equals to mRT, and then R equals to R bar by M. And next you have to remember Van der Waals equation, P plus A by V square into V minus B equals to RT. Okay. So M equals to PV divided by RT. P is what? It is 100 bar. 100 bar you have to convert in Pascal. 100 into 10 to the power 5, 5 meter cube is the volume of the gas. R is 0.2969. What we are obtaining this one into 10 to the power 3 because it is in kilo units. You have to convert in joules. Okay, into 290 Kelvin. So mass is 580.71 kilograms. Okay, density is the mass by volume. Okay, remember it's another formula. Density is mass per unit volume. Mass is 580.71 divided by 5. You're getting the density of the gas as 116.14 kg per meter cube. And one more part you have to calculate. Specific volume. Anybody how to calculate specific volume? What is specific volume formula?
So reciprocal of the density.
Correct. Reciprocal of the density. And how to find out molar volume? Molar volume, that is meter cube per kg mole.
So we divide by the number of moles, basically mass by Avogadro number is the
Mhm.
number of moles, and we divide
Mhm.
by that particular number to get the thing per
Mhm.
mole.
Correct. Okay. So this is specific volume is reciprocal of density. That is 1 divided by 116.14. You are getting the volume as 0.00861. Okay. And molar volume is given by molar volume is given by, so you have to consider the molecular weight. Molecular weight is 28 into R is 0.2969 into 290 divided by the pressure. Molar volume is, that is 0.241 meter cube per kg mole. On the other hand, volume is we are having the 5 meter cube. There is a lot of difference between volume and molar volume. Okay.
Sir, or we can multiply the specific volume by the molecular weight. We'll still get
And
the
that
same.
same thing. So whatever formula you use, you should get this final answer as 0.241. Is okay. In thermodynamics, whatever the applicable formula should apply. Okay, but you should get the final answer as the correct one. Okay.
Yes,
Even
sir.
if, for example, in case of polytropic process, okay. For example, heat transfer. Heat transfer, you can use Q equals to delta U plus W. That is the one formula for finding out the heat transfer. One more formula is there. Q equals to gamma minus N divided by gamma minus 1 into the work done. Okay, that also you can use. Okay, so you can apply any formula, but you are getting the same answer. Okay. That's why I said you have to make one chart where you write all the 5 process, write down PV diagram, TS diagram, and write the formula for what is the work done, what is the change in internal energy, what is the amount of heat transfer, what is the change in entropy, and what is change in enthalpy. These are the 6 parameters you have to write, and you have to write in a separate sheets. Okay, that's why you make 2 to 3 sheets. Write down clearly one by one, so it will be very helpful for your final exam, so that easily you can understand. So immediately after giving any process, apply the formula, and you will get the answer. Okay, that is the best way. Okay. uh, in the problem, it is description is not there. Okay, so here you see there will be 6 kilomole of hydrogen and 4 mole of some nitrogen is given. Okay, so you have to find out the general gas constant for the gas mixture. Okay, as I said, gas mixture consisting of number of constituent gas. In this problem, there are two constituent gas. One is hydrogen gas and one is the nitrogen gas. The hydrogen gas is having 6 kilomoles and nitrogen is having 4 kilomoles. So our aim is to find out the molecular general gas constant for the ideal gas mixture. Okay, so first we have to convert the mole into kg. What you are going to do in order to convert kilomole into kilojoules, just you multiply by molecular weight of hydrogen, 6 into 2. Okay, 12 kg is the mass of the hydrogen. Similarly, you have to convert 4 kilomoles of nitrogen into kilogram. Just you have to multiply by molecular weight of the nitrogen. Molecular weight of nitrogen is 28. You are getting 112 kg. Okay. Now you have to find out the mass fraction. Mass fraction is the ratio of the mass divided by total mass of the mixture. Okay. First you have to find out the mass fraction of the hydrogen as mass of hydrogen 12 divided by total mass of the mixture, that is 12 plus 112. You are getting the mass fraction as 0.0968. And one more, the mass fraction of the nitrogen is given by the mass of the nitrogen 112 divided by total mass 12 plus 112. So already we studied mass fraction, volume fraction, mole fraction in ideal gas mixture. So first we have to find out mass fraction of the nitrogen and mass fraction of the oxygen. So once you know, I derived this derivation. R, general gas constant, is summation of Yi into Ri. Yi is your the mass fraction. That is mass fraction. You have to sum up. That is Yi. That is mass fraction of hydrogen multiplied by the general gas constant for nitrogen plus mass fraction of nitrogen multiplied by general gas constant for nitrogen. Okay. So 0.0968 is a mass fraction of nitrogen multiplied by the general gas constant for hydrogen, that is R bar divided by M. R bar is 8.314 or 8314 divided by 2 plus mass fraction of your nitrogen multiplied by R bar divided by nitrogen, that is 8314.3 divided by 28. So after solving, we are getting the general gas constant for ideal gas mixture as 670.6 joules per kg Kelvin. So this kind of problem you should remember is to find out the general gas constant for ideal gas mixture. This kind of problem you see is such kind of problem is studied in ideal gas. Okay, so such kind of problems are most important. You should remember how to draw the PV diagram and TS diagram. You see, 1 kilogram of air at 1 bar pressure and 50 degrees Celsius is compressed adiabatically to a pressure of 5 bar. The air is then expanded at constant pressure to the initial volume. Represent these processes on PV diagram and TS diagram. Determine the work transfer and the heat transfer for the whole process. So whenever conditions are given, so you have to draw the PV diagram correctly and you have to analyze whether it is a compression or it is the expansion. First process is the compression process and it is the adiabatic compression. Okay, start from, you see the PV diagram, start from point 1 and it is the adiabatic compression. Okay, you have to take the compression in the reverse direction. And and then the air is then expanded at constant pressure. That's why start from point 2, it is the expansion process. That's why you have to take in the forward direction, and it is a constant pressure. You have to draw the horizontal straight line. Okay. Next, at constant pressure, next after that, it is to the constant volume to the initial point. Okay, so from 3 to 1, you join. So it is a constant volume process. Okay, see, first it is compressed adiabatically. This you have to take in reverse direction. 2 to 3 is the expansion process. You have to take in the forward direction, and then to the initial volume. Initial volume is just you join. So this PV diagram. So first formula is PV raised to gamma equals to constant. 2 to 3 is B equals to constant, and 3 to 1 is B equals to constant. Okay. So this is how to draw the PV diagrams. In exam, they'll ask such kind of problem only. So concentrate on these problems. Okay. Next, to draw the TS diagram. Okay. TS diagram is first 1 to 2. Okay, 1 to 2 is our the adiabatic process. Adiabatic process in TS diagram, it is represented by the vertical line. Okay, 1 to 2 is the vertical line. So you have to take in the upward direction, because in the compression process the temperature increases. That's why you have to take from the beginning point, and then so you have to take in the upward direction. Don't take from top to bottom. That's why I said that is a compression or expansion. In compression process, the temperature increases, and the pressure also increases. And in case of expansion process, the temperature decreases. Next, 2 to 3. 2 to 3 is our expansion process. Okay. So here 2 to 3 is the constant pressure process, and then we have to join from 3 to 1. So you remember the TS diagram, constant volume and constant pressure process are represented by same curve, but only the difference in the deviation. Okay, so a constant pressure process deviates more than that of the constant volume process. Okay, so just but you have to show the nature of diagram like this. 1 to 2 is adiabatic, the compression. 2 to 3 is our constant volume, constant pressure expansion, and 3 to 1 is our constant volume process. That's why I try to understand how to draw the PV diagram and TS diagram. Once you draw the PV diagram and TS diagram, over. Okay, so just you apply the formula and you finish the problem. First thing you have to find out the volume V1. Volume V1 is MRT1 divided by P1. You have to use the ideal gas equation. P1 V1 equals to MRT1. So 1 into 0.287 into 10 to the power of 3. Temperature is 323 because it is temperature is in degree Celsius. You have to convert in Kelvin divided by 1 bar pressure. So 1 bar is, it is 10 to the power of 5 Pascal. Okay, V1 is 0.927 meter cube we are getting. Okay. Next, we have to find out uh, T2 by T1. You remember one more formula. This is relationship between temperature and pressure. Okay. T2 by T1 is P2 by P1 to the power of gamma minus 1 divided by gamma. You remember one more formula, it's the relationship between temperature and pressure. So suppose if it is a polytropic process, same formula holds good, but instead of gamma, just you take N. Okay, so all the formula are same in case of polytropic process and adiabatic process, but only the change in symbol. That is where here we are taking gamma and there we are taking N. This is a relationship between temperature and pressure for adiabatic process. T2 by T1 equals to P2 by P1 to the power of gamma minus 1 divided by gamma. So gamma is not given. Assume gamma is 1.4 for air. For air, R is 0.287, Cp is 1.005 kilojoules per kg Kelvin, Cv is 0.718 kilojoules per kg Kelvin, and gamma is 1.4. These four values you should remember. One is R, Cp value, Cv value, and gamma value. So T2 equals to 323. One more thing, you have to put everything in Kelvin. P2 is 5 bar divided by 1 bar. Anyhow, it is a ratio. You can take directly 5 by 1 to the power of 1.4 minus 1 divided by 1.4. So temperature, can you tell me whether you are going to get more than 50 degrees Celsius or less than 50 degrees Celsius here? Can you imagine and tell me?
So can you repeat the question?
No, here we have temperature as 51 degrees Celsius, right? 323. Okay. Process 1 to 2 is our adiabatic compression. Okay. We are finding out the value of T2. Whether T2 is greater than T1 or less than T1. Remember, process 1 to 2 is adiabatic compression. T1 is 50 degrees Celsius. Whether T2 is greater than T1 or less than T1.
Should be greater, sir,
How it is? It should be greater.
because compression is going to increase the temperature naturally.
Correct. So during compression process, temperature should increase. So whatever value you are getting, T2 is it should be greater than T1. We are getting 511.57 Kelvin. Okay. Next, work done formula. Okay. So anybody, what is the work done formula for this one adiabatic process? Anyone? Can you remember what is the work done?
So P1 V1 minus P2 V2 by 1 minus gamma.
Not 1 minus gamma. It is gamma minus 1. Yeah, that's why suppose you take 1
Gamma
minus
minus
gamma,
1.
they will be get
Yes.
plus and minus differently. That's ah,
P2
No, sir.
V2. Yes, sir. When we do
hmm.
P2
Yeah.
V2 minus P1
Correct,
V1,
correct.
then it is
Okay,
1
that's
minus
why you
gamma.
should be very careful. Suppose if you one symbol also goes wrong, you will not get the correct answer. That's why be careful. Suppose if you are writing P2 V2 divided by P1 V1, P2 V2 minus P1 divided by 1 minus gamma, or P1 V1 minus P2 V2 divided by gamma minus 1. Like that, you should remember. Okay, that's why remember you are knowing the formula, but you are not doing properly. In that case, you will not get the correct answer. So be careful in writing the formula. So work done during adiabatic process is given by P1 V1 minus P2 V2 divided by gamma minus 1. So once again you are getting it as negative. Okay, negative means it is a compression process. You remember for compression process you are getting negative value, and for expansion process you are getting the positive value. Okay, and this P1 V1 we can put it in this formula also, Mr into T1 minus T2 divided by uh, Mr into T1 minus T2 divided by gamma minus 1. This also you can apply in terms of gas constant and in terms of temperature. 1 into 0.287, 323 minus 511. Anyhow, this is greater than T1. Definitely will get the answer in negative magnitude, that is minus 135.29 kilojoules. And next, how to find out V2? Okay, that's why process 1 to 2 is for adiabatic process. Apply the formula P1 V1 to the power of gamma equals to P2 V to the power of gamma equals to constant. So we know all the values. We know P1, we know P2, we know V1, but only unknown thing is V2. So apply this formula V2 by V1 equals to P1 by P2 to the power of 1 by gamma. So V2 equals to V1 is 0.927. P1 is 1 bar divided by 5 bar to the power of 1 divided by 1.4. So V2 you are getting 0.2936 meter cube. You see V1 is 0.927 and V2 is 0.2936. You observe during compression process the pressure and temperature increases and volume decreases from 0.97 to 0.936. Suppose if you are getting more than this one, your answer is wrong. That's why after getting the answer, just you compare what is the initial value and what is the final value. Okay. Next, for constant pressure process 2 to 3, you have to find out the work done. Integration of PdV. So this is a displacement work done. P2 into V3 minus V2. We are taking now process 2 to 3. That is constant pressure process. So you have to take P2, any of P2 and P3 are same, into the difference of V3 minus V2. Can you tell what is the value of V3 here in this one? In this problem, what is the value of V3?
So V3 is the same as V1.
Correct. V3 and V1 are same because it is the constant volume process. That's why I said you have to draw the PV diagram properly. By seeing the PV diagram only we can tell, and we can easily solve the problem. So P3, V3 and V1 are same. So W223 is 5 into 10 to the power 5 into 0.927 minus V2. So you're getting 316700 joules or 316.7 kilojoules. Okay, now sometimes they'll ask the net work done. Net work done is, hello. ಹೇಳಿ sir. ಇಲ್ಲ ನಿನ್ನೆ ಕಳ್ಸಿಕೊಟ್ಟಿನಿ ಸರ್ ಮೇಲ್ ಐಡಿಗೆ. ಹಾ ಪರ್ಸನಲ್ ಮೇಲ್ ಐಡಿ ಕಳ್ಸಿನಿ, ಆಮೇಲೆ HOD ಅಂಡರ್ಸ್ಕೋರ್ ಫಿಸಿಕ್ಸ್ ಅಂತಿದೆ ಅಲ್ಲಿಂದ ಕಳ್ಸಿನಿ. ಅಲ್ಲ ಅಲ್ಲ ಅವ್ರಿಗೆ ಕಳ್ಸಿನಿ ಸರ್. ನಿನ್ನೆ 3:30 ಕಳ್ಸಿ ನೋಡಿ ಸರ್. ಅಲ್ಲ ಅಲ್ಲ ಒಂದ್ಸಲ ಚೆಕ್ ಮಾಡಿ ನೋಡಿ ಸರ್, ಯಾಕಂದ್ರೆ ನಿನ್ನೆ ನಾನು 3:30 ಕರೆಕ್ಟ್ ಆಗಿ ನಿಮಗೂ ಕಳ್ಸಿನಿ, ಅಶ್ವಿನಿ ಮೇಡಮ್ಗೆ. ಇಲ್ಲಿ ನಿಮಗೂ ಕಳ್ಸಿ, ಎಲ್ಲ ಕಳ್ಸಿನಿ ಸರ್, ನಿನ್ನೆ ಕಳ್ಸಿನಿ ನಾನು. ಹಾ ಇಲ್ಲ ಸರ್, ಅವ್ರಿಗೆ ಎಲ್ಲ ಅವರೇ ಕಳ್ಸಿನಿ ಸರ್. ಹಾ ಹಾ ಓಕೆ ಓಕೆ ಸರ್. So, we are getting 187.41 kilojoules. Okay. Can you tell me how to find out the heat transfer during the process 1 to 2, 2 to 3, and 3 to 1? Anybody? Okay. Now we found out the work done. How to find out the heat transfer during 1 to 2? What is the value?
So heat transfer during 1 to 2, it's an adiabatic process, right? 1
Correct,
to 2.
correct.
So adiabatic wall cannot exchange heat, no sir.
Correct, correct.
So it should be 0.
Next, what about 2 to 3? How to find which formula you're going to find out the heat transfer during the process 2 to 3?
So for 2 to 3,
Constant pressure process.
same pressure. So just a second, sir. Sir, we use the CP value.
Correct. CP into?
Sir, MCP dt. Anyway, we know the temperature.
Exactly right. Okay, MCP into delta T. That is MCP into T3 minus T2. Okay. Okay. And CP value is 1.005. Okay. T2 we got. How to find out T3? Anybody? Unknown thing is T3.
Sir, we use the basic gas equation.
Which equation?
So P3 V3 is equal to MRT3.
P3 V3 equals to MRT3. Good. Okay, but P3 we know P1 given in the problem, P2 is given in the problem. How about P3 is not given in the problem?
P3 will be same, sir. It is constant pressure 2 to 3. So P2 will be equal to P3. So we'll calculate.
P3 we got. It is same as P2. Correct. P3 V3. V3 we have to find out. V3 equals to V1. Correct. Okay. M is 1 kg. Correct. R is gas constant. Correct. Okay. T3. Correct. So using this formula, you can find out the T3. Like that, you have to analyze the process. Once you know the T3, you can easily find out the heat transfer during the process 2 to 3. That is MCP into
dt
minus T2. Okay.
Yes, sir.
Can anybody tell what is the heat transfer during this process, last one 3 to 1, and what is the work done during constant volume process?
So work done for constant volume will be 0.
Correct.
And heat transfer can be calculated in terms of CV, sir.
Correct. Okay. MCV into
change in temperature.
Your
D1
table
minus D3.
T1 minus T3 or T3 minus T1?
T3 minus T1, sir. I
Sir,
mean,
it
no,
is
T1
T1 minus T3, I guess. Final
T1
minus
minus.
initial. T1 minus T3.
Correct. That's why you should analyze this process. It is MCV into T1 minus T3. Always you have to take the difference in the temperature as final value minus initial value. Okay, same thing we calculated here. Okay, so MCP into delta T for constant pressure process. We are getting 1109.14 kilojoules. Okay, and you have to find out Q223 is this one. Okay, so finally you have to find out the summation of the heat transfer is um, q1 to 2, that is anyhow 0. Q2 to 3 have to calculate q1 3. Okay, now whether work done, net work done and net heat transfer is same in this cyclic diagram. Anybody? Okay, whatever value we are obtaining, net heat done, net work done, and net heat transfer, whether both are same or it is different. Can you analyze? My question is net work done. You are calculating. You are getting something, some value as around 181.41 kilojoules. Are you getting the same net heat transfer or different heat transfer?
Sir, probably
Hmm.
a different value.
Different. No, wrong.
The same value, sir, because it's
Same
a
value.
cycle.
Correct. It is same
So,
value. Can you give the reason why it is same value?
so because it comes back to the initial state at the end.
Correct. Okay. So this is related to first law of thermodynamics in a cyclic process. Okay. The net amount of the work done equals to the net amount of the heat transfer. You remember. That's why you recall the first law of thermodynamics. Okay. In a cyclic process. Okay. Not non-cyclic process. In a cyclic process, the net amount of the work done is directly proportional to the net amount of the heat transfer. It's the first basics of the first law. Okay. Suppose if you are getting the different answer, it is wrong. Actually, you should get the net W net equals to net W cube. Okay, so the net amount of heat transfer and net amount of the work transfer are same. That's why you have to analyze everything. Okay, it's the type of process, the nature of curves, and then which formula are going to use, whether it is a compression or expansion, and you have to analyze the first law of thermodynamics and what is the heat transfer during the various process. Can you tell me, suppose if it is a heat transfer in polytropic process, what is the formula you are going to use? Anyone? Just you tell the formula, okay? Anyhow, these are other different formula. What is the heat transfer during polytropic process? What is the formula? Anybody? Just you tell the formula. Heat transfer during polytropic process.
Sir, it is MCV dt plus PdV.
No, that. So you are making the things complicated. It is just as you have to either use two formula, Q equals to delta U plus W1 formula. Another one is gamma minus N divided by gamma minus 1 into work done. You remember, this is the standard formula of heat transfer during the polytropic process. Gamma minus N. Anyhow, don't think that gamma, why it is in polytropic process. After deriving that derivation, we are getting this equation, gamma minus N divided by gamma minus 1 into work done, where gamma is the adiabatic index is always 1.4 and N is your polytropic index. So you get both the index in this formula. So we derived that derivation. One standard derivation is that just you go through that derivation to find out the heat transfer during polytropic process. Remember, once again I repeat, gamma minus N divided by gamma minus 1 into work done. First you are going to find out work done using the formula P1 V1 minus P2 V2 divided by N minus 1. After knowing the work done, easily you can calculate the heat transfer during the polytropic process. Okay, those who have not entered USN, please enter USN in the chat box. Hope you understood all the concepts in ideal gas and real gas. Okay. Still, all of you have to do some more exercise. So you'll get in all the textbooks. Okay, go through, try to solve more number of the problems.